Starting in 1990 with the Galileo spacecraft, scientists noticed that after getting a gravity assist as it flew by Earth, the spacecraft had a velocity slightly greater than what the model predicted. There is no accepted explanation for this velocity increase. In this video, we'll see how a new gravitational model is capable of not only predicting but to also accurately explain the phenomenon. First, let's understand how scientists measure spacecraft velocities. The best way to read an object's velocity is to use radar. A radar pulse is sent to a faraway object. The object will reflect some of the signal back. The time it takes for the pulse to return tells us how far away the object is, and the change in the frequency of the reflected signal will tell us its velocity through the Doppler effect. In deep space, this is not possible, since the objects are so far away that the reflected signal is too weak to be detected against background noise. What NASA scientists have done is something similar. Instead of sending a pulse and expecting a reflection, a message is sent to the spacecraft. The spacecraft locks into the carrier wave of the message, and it sends a message back to Earth. It could be using the same frequency or an exact multiple of the original frequency. The time for the message to return tells us how far away the spacecraft is, and the frequency shift from the original or expected frequency tells us the velocity of the spacecraft. The spacecraft is designed with an ultra-stable oscillator that can hold the carrier frequency with very little drift. The Flyby anomaly occurs because the frequency received from the spacecraft indicates that the spacecraft received a greater gravity assist than our model for Earth mass and orbital velocity would indicate. But it gets worse. Sometimes the effect is there, and sometimes it isn't. To understand how a new gravity model would explain this effect, we have to see how this model works. This model is based on the premise that space is falling to Earth. Its falling velocity is the same as the escape velocity. The boundary for this gravity bubble is the point where Earth's gravity equals the Sun's gravity. This is calculated by the distance between Earth and the Sun, multiplied by the square root of Earth's mass divided by the Sun's mass, or about 260,000 kilometers from Earth, 2/3 of the way to the Moon. This boundary will change as the planet's orbit takes it closer or away from the Sun. It is not known if this is a sharp boundary or if it has a gradient. When the spacecraft is inside Earth gravity, its time dilations are calculated relative to Earth. When the spacecraft exits Earth's gravity, its time dilations are relative to the Sun. A flyby event may take a few days. When the spacecraft receives Earth's message, its local oscillator will lock into the carrier frequency. But as it leaves Earth's gravitational bubble, the oscillator will be moving at a greater velocity through space and it will experience greater time dilations. This will lead to a reduction in the frequency of the oscillator, just a few parts per billion, which is the observed effect. From Earth, this reduction in the frequency of the received signal is seen as a greater Doppler effect from expected and interpreted as a greater velocity of the spacecraft than it actually is. When scientists listen to the spacecraft signal before it leaves Earth's gravity bubble, the frequency received is as expected and no extra velocity is inferred. Two opportunities to verify this effect will present in 2026. The first is a Psyche spacecraft flyby of Mars in May of 2026. Mars' gravity bubble extends only 130,000 kilometers from Mars. As Psyche does a Mars flyby, Earth will be positioned such that the spacecraft motion is parallel to Earth's, and a change of frequency of the local oscillator will not indicate a change in velocity away or towards Earth. The second opportunity will present in December of 2026 when Europa Clipper mission does a flyby of Earth. In this case, we can monitor the frequency from the spacecraft before and after it crosses Earth's gravitational boundary. This is a simple test that can be done with negligible cost and on a non-interference basis.